Hightech at Sikos BW. Technologietransfer leicht gemacht.
Welcome to the HPC podcast powered by Excellerat. My name is Andreas Wierse. I'm from Sikos, an Excellerat partner. And today we are in Denver, Colorado, the Mile High City, where the supercomputing 2023 starts actually right now. And we have something special, so we'll come to back to that later. For now, I would like to introduce my guest today, Niclas Jansson from KTH. He works there at the PDC Center for High Performance Computing. Welcome, Niclas.
Thank you.
What's your role in the Excellerat project? How are you related to all this?
So I'm the PI at KTH for the Excellerat project, managing the day-to-day task of our research at KTH. And I'm also the lead developer of the code Neko that is part of the Excellerat project.
Okay. So you have a team developing this, or is this mostly
yes,
you?
we have. I mean, the Neko team is actually now scattered across Europe and spread down even to Saudi Arabia.
Wow.
So it has grown pretty fast from being a KTH project to,
So you really have, you do have productive users in a way?
Yes.
Yeah. Okay. So that brings a burden with it. You have to support them.
Yes. And also the development effort, coordinating a team local at KTH, that's one thing. And then coordinating it across the globe is a different thing with meetings. And you have to learn pretty fast.
Yeah, definitely. And you obviously do, because what I indicated already, you have been nominated for the 2023 Gordon Bell Prize. And I think it's handed out every year. But it's a very high respected, high rewarded prize. And what they say themselves about it is that the Gordon Bell Prize represents various aspects of evaluation, such as the importance of target problems, performance optimization, maximum utilization of target system performance, and knowledge given for widely spread platforms. And I think the list of nominees is not really long there, right? Do you know how many nominees we have?
It's in the traditional Gordon Bell Prize, it's 6 this year. Okay. And then they have the additional climate prize, which is only 3.
Okay.
But we are in the traditional one.
You are in the traditional. So for all over the world, actually, you are among the 6 finalists. Yeah.
Yes.
Congratulations already for that.
Oh yes, thank you.
And we press our thumbs. Let's see how it goes. Can you provide an overview of the project that led to this nomination? The challenges that you aim to address.
So when they installed the Lumi supercomputing in Finland, we were part of the pilot program for the GPU partition. And in the end, you had the ability to run on the full machine. And we obtained quite good performance data. So often you look at how well is the code scaling. So you take one problem and you increase the number of CPUs, and you should then increase the performance with the number of CPUs you do. So we got what's said 80% efficiency on the full machine.
The full?
Yes, the full machine, 80%.
Okay.
And that was, this is pretty good with strong scaling up to 80%. But we started looking at the traces and the performance data and saw that we can actually do some improvements. And then in parallel, we had talked to some GPU expert at KTH, which was not in the Neko project at that time. And then we engaged them and really started focusing on optimizing the missing pieces here to get this closer to like 90 or 95% or some dream number like that. And that covers the performance part of Gordon Bell, but we need an application to make this a real thing. And at the same time, we also had been granted an extreme scale project on Lumi to addressing a physical problem in thermal convection. So think of it of a lava lamp, basically. You heat it at the bottom, and then you get some blobs that is going up and down. And there apparently is a big physical fight between the physicists here of what's happening when you increase the temperature and the turbulence there, if something happens. It's called the ultimate regime. And it has been unresolved. You cannot do this with experiments because it's very difficult. So you need to do simulations. And they're insanely expensive. So that was a perfect fit then to take the computational needs of that project with performance optimization and then address the other things that are around it, like handling the large amount of data that comes out and running these large simulations.
So, and this was the basis for the nomination. So the runs that you did for that, or the
So one should see that as the preparation for doing the Lumi project. So the Lumi project would have been conducted anyhow.
Anyway,
But we saw that we have a good case and we have good optimizations. We can use this and piggyback and getting a good submission in.
Yeah. So it was, probably not a coincidence, but it was a good fit to have both sides covered there.
Yeah, exactly. It's very nice to have a real application into this as well. So.
Yeah. And I think there were also some especially innovative approaches, some new things you tried or adapted in order to go so high to be able to reach that level.
Yeah, so the 80%, that was basically just the normal Neko without optimization. And then we developed more new ways of using the GPUs to use them more efficiently so that we can scale even better on the full machine. So in the end, we reached actually 99% parallel efficiency on the full.
99%.
Yes,
Okay.
I actually had a discussion with the student. He was doubting the data until we actually looked at the error bars and everything.
So you couldn't believe it.
We couldn't believe it. You should never get a straight line out of this at this scale. So.
Yeah. Was this based more on, let's say, pure technical aspects, let's say better programming, or did you also change your algorithms or how you implemented the physics?
Both. So we looked at the math and saw that this part can be done at the same time as this. Mm-hmm. So then we have two tasks. It happens so that one task is very, very small. It has a small problem size, which is very bad for a GPU. Because the GPU is like a bucket of water. You have to keep it full.
Yeah.
So then we realized that we can run them in parallel at the same time on the GPU. And that has never been done before. So we added both changing the numerics and then changing the parallelization strategy as well.
So really innovative. Very, very impressive. Could you elaborate a little bit on the Neko spectral element code and the significant in enabling large-scale direct numerical simulations of really fully developed turbulence?
Yeah, so Neko is from the family of what's called high-order methods. And these are really crucial to how you do this high-fidelity DNS simulation that you mentioned, because you really need there has to be very little dissipative methods. They cannot disturb the flow, and other numerical properties are very good. Because when you do DNS simulation for turbulence, for example, it's a very boring thing. It's a box, and you start blowing wind from one side, and then error can grow over time, and you have to do very long time integration. So if you don't have a good numerical method, it can just break down or actually trigger into turbulence too early. So that's good from the numeric side. The other side is that it fits very well into modern hardware. It's very good for GPUs. It's very good for recent CPUs.
And is that unique, Neko, in this context, at least of your research?
Actually, we are kind of a descendant from a code called NEC 5000. That was in the first Excellerat.
I remember,
yes.
Excellerat 1.
Exactly. So and that was a code from the 80s, 1477.
Wow. And
how Neko was born was that we had a decision to make. We saw that all the machines will be accelerators, or the big ones at least. Are we going to retrofit this into NEC 5000, or are we going to do something new? And we know that the numerics was good in NEC 5000, but we didn't want to try to retrofit support in that code. So we took the numerical methods and started a new code. So
are you still with Fortran?
Yes.
Okay, so
modern Fortran.
Yeah. Okay, so there's much more around, and so what? How does it work? Is it hybrid then?
It's no, yes and no. So if you run on CPU, everything is Fortran, and the reason we want to stick with Fortran is because our user base are used with Fortran. We're not aiming for full supporting all the old input decks, but they should be familiar with the program. We don't want to let them learn CUDA or HIP. That would be too difficult for them. So entire Neko is built in an object-oriented way. So all the different backends we have support for, CPUs, GPUs, it's just a way of creating objects and wrappers around everything. So the user, they work in Fortran, and they call a routine, and then Neko behind the scenes will then trickle down through the object tree and then suddenly call CUDA or HIP or OpenCL.
So the performance critical parts are still, so to speak, in the inner loop, so to speak, is Fortran optimized for the hardware, and you are organizing it. So could you say it's a modular approach? Or?
Yes, it's a modular approach. So it's only Fortran on CPU or vector machines, but 2 different code paths because you need to have different set of the loops. But when you go for GPU, then you actually go from Fortran via a device abstraction layer that we wrote. So we are actually be able to call CUDA or HIP from Fortran.
Okay.
So we need to go down to CUDA and HIP.
Yeah,
but the user don't have to see this. We cover it from. We hide it from.
And it allows you also. This layer allows you to be more flexible also in the future, right?
Exactly. So we can add more backends all the time. Yeah. Now the big discussion is what to do with the Intel GPUs.
So are they idling once the GPUs are busy, or it's a matter of load distribution?
I mean, the CPUs are completely idling basically. So we start it on the CPU and then we offload it to GPU.
So how does it then? The 99% are then that's. Yeah, it's not about fully loading the CPUs, but it's the scaling efficiency, right?
Yeah, scaling efficiency.
Okay. Yeah, get it. So we talked about innovative approaches, something that you also did. You took care of or worked with in situ data compression. What exactly does this mean?
Yes, so this case that we're running is very, very large. So it's going to output a lot of data. So we needed to take care of this data somehow. So the traditional approach is to ask the center to have a lot of quota for you, a lot of disk space. But that will not be workable here because it's too much data. So we then, while we're running simulation, we're actually then in situ during the simulation moving the flow field from the GPU, compress it, and then send it to the CPU. And the CPU actually then is doing some work because then it's writing it to disk. So we're doing what's called lossy compression on the GPU, and then you do a final lossless compression on the CPU.
So the compression on the GPU is not necessarily lossless?
It's lossy. Yes,
it's lossy.
Yes.
Okay.
But it's an old method we did, not in Excellerat 1, but was kind of related to Excellerat 1. It's a physics-based compression that you only take out certain modes of the simulation that you need. And so it only works for spectral elements.
Yeah. So we are not talking like JPEG artifacts or something like that, but you know exactly what you're doing, and you're just getting rid of the the not relevant parts.
Yeah, exactly. So we can actually compress everything up to 97%.
Yeah.
So it's a big reduction in data.
And at the same time, the accuracy is not really hit significantly.
That depends.
Okay.
But the error are between 5 to 2.5%, which it's okay.
It's okay, yeah. Is this a qualitative thing actually that it depends what you want to learn from the results, so.
Yes, so we actually have some knobs in the simulation. So in the simulation you can say I want, for example, this accuracy, then I can make the lossy part less lossy.
Yeah. So it's even adaptive, so to speak, in a way, or you could adapt it.
It would be excellent if it was automatic adaptive, but it's manual adaptive now. Yes.
Okay. Yeah. Well, there's probably some work that needs to be done for the next Golden Bell Prize nomination. So this in situ data compression, if I remember correctly, is already closely related to the Excellerat, right?
Yes, it's so Excellerat phase 2 started in January this year. So it would have been very good if we had results already. But this is really coming down to know-how and the in situ work done in Excellerat to connect Neko to other tools.
Yeah. So was the Excellerat partners, or what was the support that you received by the Excellerat team? Has this been a collaborative effort? Were there contributions from other institutions?
It's mostly collaborative within KTH.
Okay.
So it's the people that are part of the Golden Bell submission are the ones that are also paid by Excellerat and are in these work packages related to workflows and in situ and compression and everything.
Okay, so the close collaboration there, the physically close, was also helpful.
Yes.
And the funding of Excellerat to really
so we can keep the good people at KTH. But also that Excellerat has, in the first phase of the project, built up a lot of know-how of the simulation life cycle, how to create meshes and everything. So actually what's also contributed here was something from Excellerat 1, how to do good meshes, our special hexahedral meshes that we have. So we can create these very large and detailed meshes needed for the simulation.
Yeah. So what you say basically is we had Excellerat 1, which was already a very good project. And to be able to continue now with Excellerat 2 actually is really, really helpful. So, because often funding is only, let's say, limited to 3 years, and then you have to do something else. But here, this is built, let's say, step by step. Could you say that?
Definitely. It comes back to the important thing now that now one has to invest in software as well. And these EuroHPC project that we have now, the Center of Excellences, are really helping the European codes to actually be more ready for exascale and future architecture as well.
Yeah. So you're providing really an important part of the usability of systems like Lumi, right? Because there's not. Do you know of any other codes that really scale that high on such a system?
Of course not. No, but on Lumi, I think we are the only one who has actually scaled with that performance on the full machine.
Yeah. That's really, really impressive. So if we are looking at your research findings, what are the potential implications to the field of fluid dynamics and computational science?
Yes, so as I mentioned in the beginning, we are working in the field called turbulent convection. So it's this lava lamp thing, you're heating at the bottom and you're cooling at the top. And this relates to this long-standing question in turbulence research called ultimate regime. So very technical is you have this small turbulence at the bottom of the lava lamp, and then if the boundary layers become turbulent, and that has quite severe implication of the heat transfer. So if we can prove that there is an ultimate regime or not, we will have a better understanding on thermal convection. That has implication in chip cooling, the Earth's core, and better understanding of the sun's the mantle convection inside the sun.
So that's what you mentioned, what cannot be done today with experiments. So it's actually the only way for now to understand more.
Exactly. So my understanding, I'm a numerical analysis and computer science. I don't have the background in fluid mechanics per se, but my understanding from the experimental side here is that to do these experiments, you need to cool everything to very low temperature.
Yeah.
Yes. And then measurements will be very inaccurate.
Yeah.
So simulations are the only way, it seems.
Great. And then if you translate this into real world applications, can you see what impact that might have?
How about the ship cooling, for example? We can probably design even smaller ships with a better power envelope, for example. Energy savings there. Everything that has relating to heating and cooling and convection, indoor climate, for example, ventilation.
So actually a very wide application field, and also a very important one if we look at energy consumption, which is a big thing right now and will be.
Yeah, exactly. You really need to understand this kind of very deep physical question to actually design it in a better way, yes.
That actually covers this pretty well the application part of the Gordon Bell Prize, right? Coming back to that, we don't know yet how it will come out in the end, your nomination, but could you share a little bit your experience that you already have now, but just being nominated for the 2023 Gordon Bell Prize?
I mean, it's great. It's a big journey. Personally, there's a lot of visibility for myself and the team with our work. But also for the community, it really confirms that you need this large-scale computing for the science. And the only way to succeed here is that you need to have interdisciplinary team. So you need to have a collaborative effort to drive this forward. You cannot any longer be the lone scientist sitting at home and writing code. And and ask for time on a machine, run some simulations. This has to be a synchronous effort with all the teams and even the supercomputing centers and the Center of Excellences by EuroHPC, for example.
Great. So all the best wishes for the next days when this decision will be taken. And it's been a pleasure to discuss with you those things. And all the best also for the work in Excellerat. It will be common work. And thanks for being here.
Thank you very much.